Unplanned equipment failure costs manufacturing plants between $50,000 and $250,000 per hour, not per day, per hour. The existing solution to this problem require a cloud subscription, a reliable internet connection on the factory floor, and a per device licensing fee that can run to 20,000 rupees a month per machine. In this video, I am going to show you a system that I built that solves the same problem with a 2,000 rupees Raspberry Pi. No cloud subscription, no internet dependency, and inference latency under 50 milliseconds. Let's go. So quick orientation before we run anything. Here is the repository. So as you can see, the core files which are there in this repository are, the first one is a sensor simulator file, which basically dropped in as a replacement for the physical MPU6050 accelerometer. It generates mathematical accurate vibration waveforms for 5 fault states and publish them over MQTT. The next one is the inference engine.py. This subscribes to that sensor data, extracts the FFT features from each window, and runs them through a quantized TFLite model and publish the classification results. And the next one is the alert manager.py. This subscribes to the inference results when confidence crosses 75% on a non-normal fault class. It fires a Telegram push notification and logs the event to SQLite. And next one is the train model.py and train CWRU model.py. This one, train CWRU model.py. So these two are the training scripts. The CWRU version is the one that matters, and I'll explain that in a moment. And the CWRU simulation folder, this is where the real bearing data lives. Okay, so everything in this repository is designed around one architecture principle. The model runs on the device, not on the cloud. So before I run anything, I want to show you the physics underneath this, because this is where most student projects cut corners, and it's exactly what separates this from a generic machine learning demo. Let me show you the fault profiles. So here we are looking at the sensor simulator.py and we are looking at the fault profiles. Each fault type generates a signal with real physical frequency. Bearing wear, if you see the second one, the bearing wear is generating a sinusoid at 105.9 Hz. That's not a made up number. That is the ball pass frequency outer race BPFO calculated from an actual geometry of a 6205 deep groove bearing running at a 1750 RPM. The formula is there in the README. Imbalance, which is generating at a 29.95 Hz, that's 1 RPM frequency. Imbalance always shows up at that shaft speed. Misalignment, 59.9 and 119.8 Hz, 2 times and 4 times the shaft frequency. Misalignment produces these harmonics, and this is the standard vibration analysis. Let me show you the generate vibration function. So if you see over here in the generate vibration function, we are generating the Gaussian noise, which is basically always present in any real machine. This is the Gaussian noise. So the fault frequency which are added on the top of that noise is going to increase the amplitude. If you see this function, is going to increase the amplitude with severity. And the critical profile which you see at above, this critical profile, it's going to combine multiple fault modes simultaneously, because in real machines, faults don't come alone. Let me show you the inference engine now. So the inference engine doesn't feed on raw samples into the model. It extracts 6 features from each of the 512 sample window. The RMS, which is nothing but your overall energy of the signal, peak amplitude, spectral mean, dominant frequency, which is where the most of the energy is concentrated, spectral energy, and kurtosis, which is particularly sensitive to the impulsive spike-like character of bearing faults. These 6 numbers are what the model actually sees, not the 512 raw samples. 6 features, and that's what makes it fast enough to run it on a Pi. I'm going to briefly show you the training pipeline, and then we will move to the live demo. I won't be rerunning the training on camera. It takes about 15 seconds or so, but I'll show you the output. This one is the output. So we get basically the model.int8.tflite, the file. Okay. So you can see this is the model which is created by the training. The CWRU, the Case Western Reserve University bearing dataset, is the standard benchmark for industrial condition monitoring and research. It's real accelerometer data from physical bearings with seeded faults, and a drive end-to-end accelerometer sampled at 12,000 Hz and then resampled to 400 Hz to match the inference engine window rate. Okay. So I'm going to show you the download underscore CWRU.py. So this is a file which basically pulls all the .mat files directly from the CWRU public dataset. Okay. So this is the base URL which we need to feed it over there. It gives us 4 classes: normal, bearing, imbalance, and misalignment, and about 2,870 windows after windowing with 50% overlap, plus 600 synthetic critical faults window to give that class enough training examples. Okay. So the train model which I showed you earlier, the model underscore int8.tflite, it's only 8.6 kilobytes and it's int8 quantized. And that is a full fault detection model which less than 9 kilobytes, and that is what runs under 50 milliseconds on a Raspberry Pi 4. And one thing I worth thinking flagging out over here, I initially trained on synthetic data only and got 100% validation accuracy. But when I replayed the real CWRU signals through the pipeline, the model misqualified almost everything because that's the domain gap. The sinusoidal signal, the training signals, don't capture the impulsive, non-Gaussian character of the real bearing faults. Retraining on the CWRU data fixed that immediately. And that lesson alone is worth more than most of the ML courses. So now let's run the full system. These are the 4 terminals. The terminal number 1 on the left hand side is the MQTT broker, Mosquitto. Let's run that. Mosquitto is running, and this is the message bus that connects every component. In production, this would run on a dedicated machine or a small Linux VM on the plant LAN. And here it is running locally. Now terminal number 2, this is the inference engine. So let's run the inference engine now. So this starts the subscriber, and it's now listening on sensor or vibration and waiting for data. The TFLite interpreter is loaded, and the feature normalization parameters are loaded from the feature norm.npy, and it's ready. Now let's go to the terminal number 3. This is where the sensor simulator will run. So I'm not going to start the simulator. I'm just going to put the command. Okay, so command is there. Now let's move to the terminal number 4. This is where we will initialize the Node-RED dashboard. Okay. So now the Node-RED dashboard is running on the local at 1883 port. Okay. So now let me run the normal baseline input to the sensor. Okay. So now you can see once I trigger the normal baseline normal sensor, the inference engine starts giving the output, and this is the output which we can see in the Node-RED dashboard as well. So over here in the Node-RED dashboard, this is the flow where we need to define all the sensor and the inference and connect them to the exact vibration waveforms, motor temperature, phase current, and fault class display, confidence score, and alert history table. Okay, and this is how the Node-RED dashboard looks like. So if you see over here, the dashboard is now live. Let me walk you through what you're seeing on here. So in the top left hand side, you can see the live vibration waveform, which is 512 samples per window at 400 Hz. You can see the low amplitude, the broad noise characteristic of a healthy machine. So there is no dominant frequencies which are standing out. The fault classification is normal, green, and confidence is up to 100%, right? The model is very confident that this is a healthy machine. The temperature is coming between 40 to 43 degrees centigrade and the current is 3.2 amperes. And these are coming from the simulator alongside the vibration data. And if you see the alert history table on the left and bottom side, it's empty. We don't have any alerts right now because everything is normal. This is what a healthy machine looks like. Low vibration energy, no characteristics of frequency, high confidence or normal class. So this is your baseline. Okay. Now I'm going to inject a fault. This is where it gets interesting. Okay. So I need to kill the existing sensor data simulation. Okay. And insert the imbalance simulator data. So how do we do that? We replace the normal command with imbalance. Now if you see in the dashboard, watch the waveform. Okay. So you can see that the waveform has completely changed. We have higher amplitude, and if you look carefully, there is a periodic structure, and that's the 1 RPM frequency at 29.95 Hz showing up. Okay. On the right hand side, you can see the fault classification is done at imbalance with accuracy of 97 to 98%. So the model classified this correctly within one window, which is 1.28 seconds of data. In a real plant, this would have appeared on the screen and then it would have appeared on the maintenance engineer's phone as a notification that fault detected, imbalance. Okay. So in the alert history also you can see the imbalance is detected with the accuracy, confidence score, and the same information is now also written to the audit trail in alerts.database. Okay. Now let's move to the next fault injection, which is bearing wear. So I need to replace the imbalance with bearing wear. So you can see the inference has already started detecting the bearing wear. Let's see it on the dashboard. So this is a fault that causes the most catastrophic failures, and because it is often the hardest to detect visually, the machine sounds fine, the temperature is normal, the current draw is the normal, but the vibration signal, the model catches it, and confidence in the low 80s or 90s is fine. So bearing wear is a subtler signal than imbalance, and the confidence reflects that, right? It's showing around 98% because this is a synthetic data, right? In a real deployment, you would be getting this alert days or weeks before any conventional inspection would catch it. And that's the entire business case for the system. Okay. Now let's move and inject another sensor data, which is critical fault. How do we do that? We kill the existing sensor data simulator, and then we basically replace the bearing wear with critical. So the critical fault is the fault where multiple faults are happening simultaneously. So let's see how does it look like on the dashboard. Okay. So if you see, there are very high amplitude and multiple dominant frequencies, and the confidence is around 100% because this is synthetic data, and this is what the final stage of the bearing failure look like. At this point in a real plant, you are minutes or hours from a catastrophic mechanical failure, and this alert means shut down the machine immediately under controlled condition before it shuts itself down the hard way. Okay. So everything whatever we have seen so far has been synthetic data, mathematically accurate but synthetic. Let me show you the real data replay. Okay. So we need to kill the existing sensor information, and instead of that, what we will be doing is we will be changing the sensor. So from the synthetic sensor, we will be changing to the CWRU sensor. So CWRU, So we have to go to CWRU simulation and then simulator fault bearing underscore wear. Okay. So if you see, the system has already started detecting the bearing wear in the inference. Let's see how does it look like on the dashboard. So on the dashboard, this is actually streaming actual accelerometer recordings from a physical test rig at Case Western Reserve University. Real bearing, real fault, and real signal. The model trained on the same dataset is classifying it correctly, which is bearing wear, and the waveform looks different from the synthetic version. It is more impulsive, less sinusoidal. And this is what a real bearing fault signals look like, right? So the pipeline is completely identical. The MQTT message format is identical. The inference engine, we didn't change a single line of code. This is the value of designing a hardware agnostic data transport from the start. Okay. So before I close out, I want to make an architecture explicit because this is what recruiters at companies like Siemens, Bosch, or L&T Technology Services are actually evaluating when they look at a project like this. So there are total 3 layers in this implementation. Okay. So layer 1 is sensors. MPU 6050 for vibration, DH22 for temperature, ACS 712 for current. On a real deployment, these sit on the bearing housing. On a laptop, as in this simulation, the Python simulator replaces them all. Same as MQTT output format and 0 other changes. Layer 2, Edge AI. The feature extraction followed by TFLite inference, 8.6 kilobyte, under 50 milliseconds. No cloud, no latency, and no subscription. Layer number 3, Alert AI. MQTT to Node-RED dashboard for the dashboard, and later we can also do the integration with Telegram bot API for the push notification. SQLite for the audit log. The key design decision is the MQTT as a data bus and every component is decoupled. You can swap the sensor reader, change the model, replace the dashboard. None of it requires touching the other components. And this is how the production industrial IoT systems are actually built. For a multi-asset deployment, say 10 motors in a plant, each PI will publish to a namespace topic. Sensors slash vibration slash motor 1, sensor slash vibration slash motor number 3. The broker, the dashboard, the alert manager scale up to handle all of them with 0 architecture changes. That's the complete system. Let me recap what this demonstrates. Signal processing, which is FFT feature extraction from raw accelerometer data, using real physical fault frequencies, not arbitrary numbers. Edge AI engineering, model quantization from a float 32 to INT8, reducing a 2 megabyte model to a 8.6 kilobyte without meaningful accuracy loss. Inference in under 50 millisecond on a constrained hardware. IoT architecture, which is MQTT, PubSub, decoupled components, namespace topic, and hardware agnostic design. Real data validation. The CWRU bearing dataset, not the synthetic one, not the made up one. The real signal from the real faults. And end-to-end system integration, sensor to inference to the dashboard to mobile alert to data bus log. Every layer connected and working. The GitHub link is there in the description. You can go through the README file, and the README has a full deployment guide for both laptop simulation and Raspberry Pi hardware. The CWRU simulator folder has everything you need to replay the real bearing data through a pipeline. If you found this useful, consider star the repo. It helps other engineers to find it. And if you are working on industrial IoT, Edge AI, or predictive maintenance, drop a comment below. I read them all.